Okay, so today I want to talk about section 3.1. Extrema on an interval. And I want to start with that definition of maximum and minimum. We say a function f defined on an interval I and I can be a closed interval, it can be an open interval, it can go off to infinity in one direction or the other, it can be closed on one side and open on the other, it can be any interval you want. We say that a function f defined on an interval I has an absolute or global maximum at x equals c. C will be a value in the interval I. If f of c is at least as big as f of x for all x in, remember that symbol in, the interval I. So before we go on to minimum, so absolute or global maximum, you can use absolute and global as synonyms here. Before we go on to minimum, let me just draw you a picture. So let's say we have some function, and I will choose as my interval, let's see, we'll start here at A, and we will end here at B. So we will take I as my interval from A to B, and this is a graph y equals f of x. We're looking for an x value, which I call c, where f of c is at least as high as f of x for any other x value in my interval AB. This time I picked a closed interval. And so we're basically looking for the highest point. And on my picture, it looks like that occurs right about here. Looks like that's the top of the hill. There's x equals c. And of course, if you plug x equals c in, you get this y value. And I think you can see that this y value is at least as big as any other y value for any other x value between A and B. Hopefully that makes sense. I wish I could ask you whether or not it makes sense or not, but I'm not really in a position to get an answer from you. So likewise, we say f has an absolute, and again, you can use the word global, minimum at, let's say, x equals d, if f of d is less than or equal to f of x for all x in the interval I. And again, d must be in your interval too. So coming back to this picture, on my picture we're looking for the smallest y value corresponding to any x value between A and B. And to me it looks like it's all the way on the right-hand side. That my d in this case would have to be exactly the same as b. That's an equal sign. D and b are the same. And this is going to be f of d. If I plug b or d or whatever you want to call it in, I get that y value right there. And that's lower than any other y value for any x value between A and B. So an absolute maximum the biggest that the function can get in the interval, and the absolute minimum, the smallest that the function can get in the interval. So I have a question for you. Is it possible to have an interval I and a function defined everywhere on I so that f has no maximum nor minimum. And when I say maximum or minimum, I mean an absolute maximum or an absolute minimum anywhere on I. There's no highest point and there's no lowest point. So remember, I would like you to think about this question a little bit, and unlike being in class, you can pause the video whenever you want. But in the meantime, I'm going to erase the blackboard over here while you think. So I'm not quite sure what your thoughts were on the matter, but as a matter of fact, the answer is yes. The answer to this question is yes, and I'll give you some examples. Let me pick as my interval negative infinity to infinity, the whole real line. That is a perfectly acceptable interval. And I will take a perfectly simple function, f of x equals x. You know what the curve y equals x looks like. It's a straight line going uphill at 45 degrees and crossing at the origin. So y equals x. There's no x value where I can be at least as high as every other point, because no matter where I stand on this curve, I could always move to the right and be higher yet. The y value could get bigger. There is also no lowest place on that curve. There is no x value where the y value is at least as small as every other point, because no matter where I stand on that curve, I could always move to the left and be lower than I was. I can only draw a finite section of the curve because my blackboard is finite, but that curve goes on forever to the right and to the left, and infinitely high and infinitely low. So you might think, oh, well, that's a bit of a cheat. I used an infinite interval. Could you do it with a finite interval? Is it possible to have a function defined everywhere on a finite interval with no maximum and no minimum? Again, please feel free to pause and think about that question. I think it's an interesting question. But once again, the answer is yes. Let's let my interval this time be the open interval between 0 and 1. And I'm going to choose exactly the same function I had before. Call it g this time. So this time on this interval, I'm only going between 0 and 1 on the x-axis, which means my y values are only going between 0 and 1. And I just have a little piece of this curve, the part between 0 and 1. Part between x equals 0, y equals 0, and x equals 1, y equals 1. Because it's an open interval, I don't include the value at x equals 0 and the value at x equals 1. Those 2 points are not part of this curve. And you can see that there is no highest place on this curve, because let's say I'm standing at x equals 0.9, then my y value is 0.9. Is that the highest value? No, I could move a little bit to my right. I could go to 0.99, and I'm higher yet. My y value is higher. And then I could go to 0.999. My y value is higher. I've moved up further on the y-axis. But I can't stand at 1 because I have the open interval between 0 and 1. 1 is not in the interval, so I can't stand there. Likewise, there's no lowest place on the interval. I can get closer and closer and closer to x equals 0, which means my y values get closer and closer and closer to 0. But I can't stand at 0, so there is no highest place and there's no lowest place in the interval. Now again, you might say, well, that's kind of a cheat, because even though I didn't use an infinite interval, I used an open interval. Let me ask you the same question. Is it possible to have an interval, this time a closed interval, and a function defined everywhere on the interval? It has to be defined everywhere, where the function still has no maximum and no minimum. Again, think about that question, see if you can come up with an answer. Maybe it's yes, maybe it's no. If you think the answer is yes, there does exist such a function, you need to come up with a function. If you think that the answer is no, there are no such functions, you need to think of a reason. Once you're thinking, I'm going to erase what's on the blackboard over here. Again, the answer is yes. This time, it's a little bit more work to define and to draw. So I am going to take the interval, this time the closed interval 0, 1, and I will take the following function. I'm going to draw it first and then show you what the definition of the function is. We really don't need an algebraic definition of the function. I'm going to give you one anyway, but I think a picture will explain this perfectly nicely. Okay, so here is going to be 1, and here is going to be 1. I'm just going to dot in some lines here so I can see what I'm doing. And here's height 1/2, and here's x equals 1/2, and I would like my function to look like this. Starting at 1/2, going up to 1, but at x equals 1/2, I'm going to have an open circle, and I'm going to have another open circle down here at x equals 1/2, and bring it over here. And at x equals 1/2, I am going to define the function to be height 1/2. You can see that's a perfectly nice function. It passes the vertical line test. At every single x value, we draw a vertical line. It crosses the curve just once. So let's see, I promised you a formula for this. This function is going to be x plus 1/2 if x is between 0 and 1/2, where that's a less than or equal to, and that's a less than. That gives me a piece of that line, just the part between x equals 0 and x equals 1/2. It equals, let's see, x minus 1/2 if x is bigger than 1/2 and less than or equal to 1. That gives me the line x minus 1/2, y equals x minus 1/2, but I only want the piece between x equals 1/2 and x equals 1. And right at x equals 1/2, the value is 1/2. This is certainly not the only option, but it is a perfectly nice option. If you take a look at this curve, you will see that between 0 and 1, which is my interval, closed interval 0 and 1, there is no highest point. As I move closer and closer to 1/2 in this direction, I'm getting higher and higher and higher. But at x equals 1/2, I can stand there, but I'm not up at height 1. I'm down here. Likewise, you can see that as I move closer to x equals 1/2 from the right, the values get lower and lower. But I can't stand at x equals, if I stand at x equals 1/2, I'm up here. So there's no highest place. This thing gets y values as close to 1 as you want, but not at 1. And there's no lowest place. We have y values as close to 0 as you want, but not at 0. So I want to sort of continue next time with a version of this question. Under what circumstances on an interval I and a function f, can you guarantee that f has an absolute maximum and minimum on the interval I? That's where we're going to begin the next lecture. But before we break for today, I want to give you one more vocabulary bit. So an extremum is a maximum or a minimum, which explains the title of this section. Well, it sort of does. Maximum is a singular. The plural of that's not maximums, it's maxima. Minimum is singular, minima is plural. And extremum is singular, extrema is plural.